All right, let's get right into it. When you strip everything else away, a database really only has two jobs. First, you give it some data, and it has to store it somewhere safe. Second, when you ask for that data back, it needs to find it and give it to you, fast. Now that sounds pretty simple, right? But figuring out how to do that well, especially at a huge scale, is one of the coolest and most important challenges in all of computer science.
You know, there's this fantastic German proverb that just perfectly nails the problem we're talking about. It basically says that being super organized is just a sign that you're too lazy to search properly. And this really gets to the heart of the trade-off that defines how databases work. Do you put in the hard work up front to keep everything perfectly organized? Or do you just throw it all in a big pile and accept that you'll have to work harder to find things later?
So to really understand this, we're going to start at ground zero. We're going to build the absolute simplest database imaginable. This is going to help us see the fundamental problem that all those complex, fancy database engines out there are really trying to solve.
Okay, check this out. Believe it or not, this is a fully functional key-value database, and it's written in just 2 lines of a bash script. The first function, dbSet, is as simple as it gets. It just takes a key and a value and tacks them onto the end of a file called database. Done. The second one, dbGet, searches that file for whatever key you give it and returns the last value it can find for that key.
And right here we see that core trade-off in action. Our dbSet function is super fast because just adding a line to the end of a file is a really efficient thing to do. But dbGet, well, that's a whole other story. It has a massive performance problem. To find any key, it has to scan the entire file from the very beginning to the very end every single time. We call this an ON operation, which is just a formal way of saying that the search time grows in a straight line with your amount of data. If your database gets twice as big, your lookups take twice as long. That's a recipe for disaster.
So, how do we fix this slow lookup? The answer is an index. The best way to think about it is like the index at the back of a textbook. It's a separate, special structure that tells you exactly where to go to find what you're looking for so you don't have to read the whole book. But, and this is the crucial part, there's no free lunch. An index makes our reads way faster, but it also slows down our writes. Because every time we add new data, we have to update the index too. This is the fundamental trade-off of databases.
Okay, so let's dig into the first major philosophy for building these indexes. It all starts with a really simple, almost radical idea. What if we just only ever add new data? What if we make a rule that we can never ever change or delete data that's already been written? This is the core idea behind something called an append-only log.
And here's how it works. When a new write comes in, it's just appended to the end of a log file on the disk. Simple. The real magic happens in memory, where we keep a hash map. You can think of it like a phone book that maps every single key to its exact location or byte offset in that big log file. So when you want to read a value, you just look up the key and the hash map. It gives you the precise address on disk, and the database can jump straight to it. It's incredibly fast.
Now, you might be thinking, wait a minute, doesn't that log file just grow forever? And it would, except for this really clever process called compaction and merging. In the background, the database is constantly tidying up. It takes chunks of the log, called segments, merges them together, and while it's doing that, it throws away any old, outdated values for a key, keeping only the most recent one. This keeps the database from running out of disk space and keeps lookups nice and fast. Now we can make this even more powerful with one small but really significant change. What if we require that within each of these segment files, all the key value pairs have to be sorted by the key? This simple rule creates a special kind of file that we call a sorted string table, or an SS table for short.
And the real genius of sorting the keys is what it lets us do with our in-memory index. We don't have to keep every single key in memory anymore. Instead, we can use what's called a sparse index. We only need to store some of the keys as signposts. For example, if you're looking for the key handiwork, and your in-memory index says handbag is at one location on disk and handsome is at another, you know for a fact that your key must live somewhere on the disk between those 2 points. It's a huge win for memory usage.
This all comes together in a data structure that powers a ton of modern databases, the log-structured merge tree, or LSM tree. Here's how it flows. A write comes in and gets added to a sorted data structure in memory called a mem table. When that mem table gets full, it's written out to disk as a brand new, perfectly sorted SS table file. All the while, a background process is merging and compacting the older SS table segments. So when a read request comes in, the database just checks the mem table first, then the newest SS table on disk, then the next newest, and so on, until it finds what it's looking for. It's a fantastic design, especially for systems that have to handle a ton of writes.
Okay, now let's switch gears completely. The second major philosophy for databases is pretty much the exact opposite of what we just saw. Instead of only ever appending to files, this approach treats the disk as a collection of fixed-size blocks that can be read, changed, and written right back to the same spot. Welcome to the world of B-trees. This is the data structure that has powered almost every traditional relational database for decades. The core idea here is to break the entire database down into these fixed-sized blocks or pages. Instead of one long continuous log, think of it more like a highly structured library of index cards that you can pull out, scribble a change on, and then put right back where you found it.
Let's just walk through a quick example of a B-tree lookup. You always start at the very top of the tree, at what's called the root page. This page doesn't have your data, but it has key ranges that act like signposts. So, if we're looking for key 251, the root page might say, anything between 200 and 300 is that way. You follow that pointer to a child page, which narrows it down even more, maybe to the range 250 to 270. You keep following these pointers down the tree, narrowing the search at each step, until you finally hit a leaf page at the bottom. And that's where you'll find the actual key and value.
So when you put these two approaches side by side, the trade-offs become really clear. LSM trees are usually way faster for writes, because they just write sequentially to a log file. B trees can be slower because a single write might require updating several different pages all over the disk. On the other hand, B trees are often faster for reads because any given key exists in exactly one place. With an LSM tree, you might have to check a few different files to find the most recent version of a key. This also means B trees tend to have more predictable performance, while LSM trees can sometimes have latency spikes during those big compaction jobs.
So we've got these two totally different ways of building a database. Why do they both still exist? Why hasn't one just completely taken over? Well, the answer is that they're optimized for fundamentally different kinds of jobs. We can basically split all database workloads into two big categories: transactional and analytical.
Transactional systems, or OLTP, are the engines that run our day-to-day applications. Think about an e-commerce site, an ATM, or a booking system. They handle lots of small, fast reads and writes. Analytical systems, or OALAP, are all about business intelligence. They answer big questions by scanning millions or even billions of records at once, like, what were our total sales by region for every product last quarter?
Now, those massive queries and analytical systems, the ones that need to scan huge portions of a table, are basically the kryptonite for both B trees and LSM trees. Those structures are amazing at finding a needle in a haystack, finding one specific record very, very quickly. But they are terrible at scanning the entire haystack. For that kind of work, we need a completely different storage design. And that solution is columnar storage. See, most databases are row-oriented. They store all the data for row 1 together, then all the data for row 2, and so on. Columnar databases completely flip that on its head. They store all the values for the date column together in one block, all the values for the product column together in another block, and so on for every column.
The benefit of this is absolutely massive. Think about that sales query again. It might only care about 3 columns out of 100: date, product, and sales amount. A columnar database only has to read and process the data for those 3 columns, completely ignoring the other 97. This makes those huge analytical queries orders of magnitude faster.
Okay, let's wrap this all up. We've looked at append-only logs with LSM trees, updatable pages with B trees, and columnar storage for analytics. So what does this actually mean for you when you're starting a new project and you have to pick a database?
The most important thing to take away from all this is that there is no best database engine. It all comes down to your specific workload. If you're building a system that's just getting hammered with writes, think metrics or event logging, an LSM tree design is probably your best friend. For a general-purpose web application with a healthy mix of reads and writes, a classic B tree is a solid, predictable, and battle-tested choice. And if you're building a data warehouse for analytics, you absolutely need a columnar store. Using the wrong tool for the job is a surefire way to run into major performance headaches down the road. In the end, it really boils down to this one simple metaphor. The append-only, log-structured approach is like keeping a journal. You just chronologically write down everything that happens. The updatable B-tree approach is like a meticulously organized filing cabinet. Both are incredibly useful, but for very different reasons. So the next time you choose a database, the real question you should be asking yourself is this: are you building a journal, or are you building a filing cabinet?